Good afternoon, everybody. Welcome to this afternoon's session. So we'll have three speakers on deck, and the first is Justin Finkel from the University of Chicago. His field is computational and applied mathematics, and he has done his practicum at Los Alamos National Laboratory.
All right, thank you. So today I'll be discussing a statistical method to extract long-term climatological statistics of extreme weather events using short weather simulations. And this is joint work together with my advisors at the University of Chicago and NYU. All right, so brief outline. I'll first discuss the general importance and difficulty of studying extreme weather events and focus on a specific application of sudden stratospheric warming. I'll present a general method for computing some of these long-term extreme weather statistics and apply it to a hierarchy of sudden stratospheric warming models. All right, so first of all, in general, we've heard about this before, but extreme weather is very difficult to quantify for this fundamental reason that it occurs rarely. And you can see this by analogy, just thinking about if we have a biased coin with a 1% chance of heads, we could flip it 100 times, and on average, we would expect to get one head, but we could easily get 0 heads or 2 heads. So if we're trying to estimate this probability without knowing it a priori, there's a huge relative uncertainty. And for the exact same reason, if we care about extreme weather events, like a once-per-century storm, if we have a 100-year observational record, there's a huge relative uncertainty. We could expect to get one storm, but we could get 0 or 2. So it's really hard to estimate even the rates of these extreme events, let alone the more complicated statistics like the onset and the development and the impacts. So that's the basic problem. And in climate science, of course, we augment historical data with numerical simulations. But there's this classical trade-off we've heard about already this week, where you can either run a short simulation at really high resolution, as is done in operational weather forecasting, or you can run a long simulation at very coarse resolution, as is done in climate modeling. And as Ryder discussed yesterday, we need really high resolution to resolve those extreme events well. So we want to get to the upper right corner of this space. But it's hard, but this is what our statistical method aims to address, to use these weather models for these long-term climate statistics. All right, so let's talk about an application. Sometimes there are cold air outbreaks in the mid-latitudes during the winter, like in Chicago in 1985, like the ground totally froze over. In the UK, 2009, record-breaking snowfall. Just really extreme, deep freezes for a few days during the winter. Widespread disruption to transportation systems. And these two events, they occurred in different parts of the Earth, but they were both related to this single large-scale circulation pattern known as the stratospheric polar vortex. So the stratosphere is the second layer of the atmosphere. It starts about 10 kilometers above the ground. And many recent dynamical modeling and observational studies have shown that there's a dynamical linkage between the stratospheric polar vortex and mid-latitude weather, specifically like through the jet stream. The jet stream can meander, and that's what steers the storms, and it can affect these cold extremes. And to illustrate the dynamics of this, I want to play two movies in parallel to show what a winter season looks like. So I'm showing here the geopotential height at 10 hectopascals on October 1st of 2 different years, all right? And what you'll see as I play these two videos is that a vortex will develop in the middle. You'll see it as a blue dot. And it'll strengthen during the fall, and it'll decay during the spring. At least that's what you'll see on the right. That's the normal, healthy winter vortex life cycle. On the left, you'll see the development in the fall, but a sudden early vortex death in the middle of January. So let's see what happens. The vortex is developing. It's looking pretty strong. It's December, January. Oh, there goes the one on the left. It's gone. And it doesn't really recover for the rest of the season. That was really sudden. I'll play it one more time. All right, strong vortex developing. They look pretty much the same. And then just suddenly, it just splits in half, and it disappears. So that splitting event is a classic example of the sudden stratospheric warming event, which I'm going to study. Now, to quantify that, there's a few standard indices for measuring the vortex strength, like the zonal mean zonal wind. Zonal means east-west velocity. So if we plot that over time for this winter, it strengthens during the fall, and then it suddenly collapses during the winter. So the wind strength the wind is reversing direction even. And this comes along and This comes along with a rapid increase in the temperature over here. That's why it's called a sudden warming event. All right, and what I'm showing here is reanalysis data from the European Center for Medium-Range Weather Forecasting. So it's basically the observational record smoothed with climate models. And so this is a big departure from normal behavior. Okay, so the background gray envelopes are the middle 40, 80, and 100 percentile ranges. And so typically it strengthens and weakens, but this winter was very anomalous. And so the sudden warming in particular is defined by when the wind reverses or goes below a certain threshold marked by red during the winter time in blue. Although I actually want to study a range of thresholds to sort of distinguish the rates of events with differing severities. Okay, so I want to get the rate of crossing of each of these levels. But the problem is that the historical record, as you can see, is very spotty. This is the tail of the distribution. It's not well sampled. For that reason, we want to recruit these extra data in the form of hindcast ensembles. All right, so a hindcast is like a forecast, like a weather forecast, except it means that you take today's version of the model and you initialize it on a past weather date to see how today's model would have performed if it had been deployed in the past. And so ECMWF produces these. There's a whole 21-year, for every updated model version, they run it on weather for the past 20 years. And so I'm showing a couple examples in these purple trajectories. So it's initialized, and then these ensemble members spread out due to initial perturbations and stochastic physics. And they explore more of the phase space than the real world actually performed. And there's a lot of extra data which will allow us to sample these negative tails more completely. All right, so I want to talk about the quantities we want to measure, the summary statistics, or in this case, wintry statistics. First of all, will a sudden stratospheric warming happen this year, and if so, when? These are questions about weather forecasting, what the hindcasts are supposed to answer. But then there's the climatological question of how often does sudden warming happen, counting the number of years. That's a climate question, and that's typically done by counting the historical record. But what we want to do is use those short, high-fidelity weather forecasts to answer the climate question. All right, so let me go into the method. This method is called Markov state modeling. It's really basically the same version of analog forecasting. And you can picture it as follows. So if you picture the atmosphere as a high-dimensional state vector evolving through time, wind, pressure, temperature, et cetera, all over the Earth, we get a bunch of these partial trajectories, as I'm showing. None of them last the full season, but they sort of overlap. What we can do, I didn't say this before, but we can't use these short simulations directly to estimate the sudden warming probability because it stops. It only goes for 47 days. It doesn't, we don't know what would have happened if it had kept going. So we construct this model by clustering the data at each time step into a discrete number of boxes. And then we can coarse grain the dynamics as a Markov process by just estimating a transition matrix by counting the transitions from one box on today to another box tomorrow. And given the sequence of transition matrices, we can sort of query the dynamical statistics of the process cheaply. And I'll make a remark about the feature space. I've used here a very simple feature space for clustering, just the zonal mean zonal wind augmented with time delays. But there's a lot of room for improvement for finding feature spaces with machine learning techniques representing the data differently. But this is like the simplest version of it. Anyway, once we have these matrices, the rate calculation is very simple. We just need to compute a couple of ingredients. I'll gloss over this a little bit. We need to find a committer probability as a function of time, the probability of a sudden warming between now and the end of winter. We can do this with a backward pass through time because of this recursion relation. That's what the committer looks like. It just measures how close we are to this extreme event. We also need a time-dependent probability distribution, just evolving the initial density at time 0 all throughout the winter. This is really the Fokker-Planck equation. And then once we have these things, we put them together to get a rate. We just do a few matrix vector multiplications, and let's check out what the results. So this is what we get from just counting historical observations. Okay, so this is 21 years of reanalysis. It's the rate as a function of the zonal wind threshold. So as we go to the left, it gets more extreme, and the rate gets lower. That's the 21-year estimate. With 70 years of reanalysis, a longer period, we get a systematically lower estimate. So it seems like the last 20 years were more rich in sudden warmings. But what happens when we apply the statistical method to the short weather forecasts spanning the same 21-year record? Interestingly, we get a set of rates that are closer to the 70-year climatology than the 21-year climatology. So somehow the model is inferring these longer-term equilibrium statistics, even though it was initialized from a systematically different climate. And to specify more this data set, when you add up all the ensemble members and the duration, we get 900 simulation years out of this, even though they only span a 21-year period. That's why we can get a lot of data and smaller error bars as well, which come from bootstrapping, resampling different sources of data. The results look a lot more clear on a log scale. So, I show that in this upper tail, we get sort of good agreement with the long-term climatology. But extrapolating into the tail, the short trajectory method with the S2S data set, those are the short hindcasts, we get more precise estimates farther into the tail of like once per 500-year rates. All right, so I'll emphasize this is like a rate according to the model. Like it's the climatology implied by the weather model. And not necessarily that it's the ground truth, but it's a way of evaluating an important statistic, a key feature of a model. All right, so to recap, these climate statistics, we can estimate them from short weather forecasts, even though they take place over a long time span. And there's lots of questions we could ask, data-limited scientific questions about the dynamical differences between different kinds of events and what are the precursors and what are the causes of these events? Can we really extract physical meaning from these data-driven methods? And this opens up important computational opportunities for parallelized climate simulation, running many short high-fidelity models instead of a single long, low-resolution model. And so I want to do a brief demonstration on an idealized stratospheric model to dig a little bit more into the details. I'm not sure how much time I'll have, but I'll just go over a couple of the key points. So this is from an earlier project I did, demonstrating this computational technique further. If you're a stratosphere expert, feast your eyes on this slide, but otherwise, I'll just point out this. I have a 75-dimensional ODE, a simple model for the stratosphere. It's perturbed by stochastic noise to represent unresolved processes, and we get transitions between metastable states. And we want to infer sort of the rate of these transitions only using short trajectories. And so there's a few quantities of interest we have to compute. I won't really, so these quantities, they specify sort of the progress towards the extreme event from the strong vortex to the weak vortex, the committer probability and the lead time. So I've projected it into 2 dimensions. They look like this, different notions of progress from A to B. But the computational point is these are both solutions to partial differential equations over the state space, which is a 75-dimensional state space. You can't apply classical PDE methods to that, and definitely not to billions of dimensions in a climate model. So that's where this under the hood, that Markov state model that I mentioned, that's really a high-dimensional PDE method under the hood. And so to solve it, we need to overcome the curse of dimensionality. So the committer obeys a boundary value problem, a PDE, looking like this, where L here is called the infinitesimal generator of a stochastic process. It takes the form of a partial differential operator. And initially, we just solve this. We start to solve it as in a traditional Galerkin method. We expand this in a basis with some basis functions and unknown coefficients. And again, these are functions over the model state space. We apply the equation. We cast it in a weak form by taking inner products. And the key here is we have to estimate this high-dimensional integral to get these matrix elements. And we are going to estimate that by Monte Carlo simulation for a high-dimensional integral. And so what that amounts to is, due to the law of large numbers, we can estimate this integral by sampling initial conditions according to this sampling measure mu, and estimate the integral by a sum. And so physically, this means seeding initial conditions all over state space, where, again, A is the sort of strong vortex, the normal weather, and B is the extreme event. We seed initial conditions everywhere. We launch a short simulation from each of these ones. This gives us, this is an embarrassingly parallel operation. And then we sort of estimate these tendencies and estimate the inner products, and therefore recover an approximation to those committer and lead time functions, and we can estimate the rate. So this is just a more mathematical explanation. We've done some numerical benchmarking of this. We don't get perfect results, but it's sort of in the right ballpark. There's still lots of room for improvement, with which other members of my group are looking into error analysis for this method. And yeah, most importantly, we can answer scientific, data-limited scientific questions with this method, like visualizing a distribution over path space. I don't really have time to go into the details here, but this is like the early stage of sudden warming. This is the late stage of sudden warming. It's really slow at the beginning and explosive at the end. And yeah, I have hopes for applying this to many kinds of events. Okay, and I just want to finish by thanking the many people who helped me through this, my advisors, my collaborators, the Courant Institute at NYU and UChicago for allowing me for hospitality, and the CSGF for the financial support and professional community and the flexibility to pursue this interdisciplinary research. So thank you very much. I'll leave it with something.